Welcome. We are going to continue our discussion of Newton's laws and Unit 2, and we're actually going to wrap up Unit 2 in this lecture and start introducing the very beginning of Unit 3. So I promised you one last example where we are going to apply Newton's laws, and so I thought we would do a little bit of a real life one here where we're going to figure out the angle of the Duquesne incline. So based upon the following information, it's possible to figure out what the angle is going to be. It may not seem like much, but if we think about the mass of the inclined car and the mass of the counterweights, it turns out to be sufficient. So how can we go about doing this? Well, actually, if you think about what's happening here, it's the same problem that we did last time. So although I promised you another problem, this is really sort of the same problem. We're just solving for something different here, slightly different here, in the sense that we're taking a real life example. But we're doing the same sort of thing where we want to know what this angle is. And instead of adjusting that angle, we are taking it to mean that we've already accounted for what the counterweights need to be in order to make this incline go up and down at a constant speed. So this is like my incline here, and this is my counterweight. And given that I've already tuned this so that it's going at a constant speed, I want to know, what does that mean about this angle here, theta? Okay, so we can follow the same approach that we did before, and we can call the counterweights mass 1, and we can call the incline mass 2. And then the free body diagrams will be basically the same as what we did before for mass 1. When we had this sort of problem before, we had the tension force pointing up, and we had the weight force pointing down. These are going to be equal to one another because we're moving at a constant speed. So when I sum the forces in the y direction using this kind of traditionally oriented coordinate system, then I get tension minus the weight force. If it's moving at a constant speed, then this is equal to 0 since there's no acceleration. And so that just tells me that the tension equals the weight, which is going to be m1 times little g. Okay, no surprises there. So for mass 2, the picture may look a little different just because in this example I have the incline going off at this angle. When we did the previous example, we had an inclined plane in this direction. But it's really the same idea. So with it oriented this way, we've got our tension force pointing up the incline, or normal force perpendicular to that, and our weight force straight down. So this is weight 1 and this is weight 2. Okay, for this free body diagram, just like we did in the example last time, we decided to use a tilted coordinate system so that we do not need to resolve 2 of the 3 of these vectors into components. And really we aren't going to even need one of the directions here. Really all we really want to get at this angle theta. And last time we wrote out all of the directions, but based on what we already know, it turned out we only used this one in the x direction. So let's sum the forces in the x direction. We've got the tension force pointing in the positive x direction, and then we've got the component of the weight force in the x direction down, negative x direction. So that's going to be equal to m2g times sine of theta. All right, those are all the forces acting in the x direction. They're also going to sum to 0 since there's no acceleration. And I can now solve for this, saying that tension equals m2g sine theta. And just as we did before, we've got two equations both for tension. We can equal them to one another, right? Or you can think about substituting the left-hand one into the right-hand one. And when you do that, you will get that m1 times g equals to m2g sine of theta. The g's cancel. And that tells me that the ratio of these masses is what's going to equal sine of theta. And that ratio turns out to be 1/2. If you've memorized some of your common angles, you know that that means that theta is going to equal 30 degrees. Okay? So that's my claim that theta is equal to 30 degrees. That's the angle that the Duquesne incline heads up Mount Washington or down Mount Washington. And just to show you that this is accurate, here is a Wikipedia article in which you can see that the angle of the incline is known to be 30 degrees. Okay, and with that, we're basically done with Unit 2, and we're ready to introduce Unit 3. Now, Unit 3's title is Work and Energy, or Energy and Work. We're actually going to start by exploring the concept of work. Work is going to have to do with applied force on an object and also the displacement of that object. And we're going to eventually uncover how work is related to energy. So let's first start by defining work. If you have a situation where you are applying a force to an object, as you see here, those of you who may be familiar, this is a picture of people pushing a Volkswagen bus from the movie Little Miss Sunshine. But it could be any object. You're applying the force to the object, and the object is being displaced. So if I want to know what the work is that was done on this object, I'm going to perform a dot product or a scalar product. So if you can recall back to Unit 1, we learned that the scalar product returns back to us a scalar quantity. So that tells us right off the bat that work is not a vector quantity like force was. It's going to be a scalar quantity. And the amount of work then is just basically the exercise of computing this dot product, which is going to be the magnitude of the force, the magnitude of the displacement, times cosine of the angle between them. Okay? The units of work are called joules, but we can figure out what those equal. Based on this equation, I've got a force times a distance times a unitless thing, this trigonometric function, and so I've got that joules must be equal to a Newton times a meter. Newton for force, meter for distance. And if I really want to boil that down to fundamental units, remember that the Newton equals the kilogram times the meter per second squared, so a joule can also be written as a kilogram times a meter squared per second squared. Okay? Now, even though work is a scalar quantity, it can be positive or negative, right? If I plug, for example, a theta value in here, which is less than 90 degrees, then it's going to give me a positive quantity. If I plug a value in, let's say between 90 and 180 degrees, then I'm going to get, a negative quantity for my work. And you can think about it this way. What if instead of I was pushing this object and getting it to move forward like you see being depicted here, what if suddenly I got it going, and now it's going a little too fast, and I want to now try and prevent its motion, and maybe now I'm going to apply a force like this. But let's say that it's still being displaced this way. Now you see that my force vector and my displacement vector are 180 degrees opposite to one another, right? So that's going to give me a negative sign for my work because I'm trying to work against the displacement. Okay, so based on that sort of reasoning, let's take a look at the following cases. Now, of course, this isn't an exhaustive list of all the different orientations you can have for force and displacement vectors, but here are some ones for us to think about, some food for thought here. What we want to do is rank these cases based upon the most negative work to the most positive work. Okay, so as usual, you can pause the video, see if you can work it out. When you come back now, let's take a look at the limiting cases first. So this case 4 is pretty much kind of what I showed you on this previous slide, where the force and the displacement are 180 degrees pointing in opposite directions. So theta here is 180 degrees. So that's going to give you the most possible amount of negative work, right? If work equals force times distance times cosine of theta, plugging in theta equal to 180 degrees there will give me a -1 times force times distance. So that's the most amount of negative work that you can have, right? The most positive amount of work you can have would be case 1, where theta is equal to 0 degrees. All of the force that you're applying is going into the displacement in that same direction. Your angle is 0 degrees, and so that's going to be the most positive amount of work. Okay, so of the choices here, I want case 4 to be the most negative and case 1 to be the most positive. That really already narrows it down to choice D, but let's see if we can make sense of the rest. So in case 5, I see that the force and the displacement are at right angles to one another. Theta equals 90 degrees. In that case, if I plug 90 degrees into this formula here, then I'm going to get work equal to 0, right? And then case 2 and 3 are sort of intermediate cases. Case 2 is fairly close to the most negative that I can get. That is sensible because it's the next one in this sequence here. And case 3 is close to case 1. So that's why our order of 4, 2, 5, 3, 1 makes sense. All right, so go ahead and stare at that a little bit longer if it's not quite clicking for you, but hopefully you can see when you think about those limiting cases why it has to be that way. In fact, here's a nice summary of when we should expect positive work, the most amount of positive work, the most amount of negative work, and the 0 case where we have the force being applied at a right angle to the displacement. Okay, so let's do an example where we consider the net work on something. If there's more than one force being applied to an object, we've got to account for the work being done by each of those forces. And then we can sum them all together, obeying the positive and negative signs, and determine what the total work or net work is on that object. So let's suppose that we have some box which is sliding down an inclined plane. The particulars of the mass of the box and the angle of the inclined plane are listed here, as well as the frictional coefficient. Now, one thing to keep in mind is that this angle of the inclined plane is not the same angle that appears in this equation, force times distance times cosine of theta. This theta in this equation is the angle between the force vector and the displacement vector. Do not get that confused with the angle of the inclined plane. Just to make sure that we don't do that, why don't we call this angle phi? Okay, so moving on then, we want to start by drawing a free body diagram of the box that is sliding down the inclined plane, because we need to examine all the forces acting on it in order to determine the work done by each of these forces and thus the net work on the box. Okay, so go ahead and think about which of these free body diagrams makes sense. When you come back, let's go ahead and eliminate choice C. Why? Because the weight force is not pointing down, so that cannot possibly be. We can also eliminate choices D and E because we need the normal force to be acting perpendicular to the plane. The normal force is not necessarily pointing straight up unless I have a flat surface, but we're on an inclined plane here, so we want the normal force acting perpendicular to that surface of the plane. Only choices A and B are going to give me that. Now the question then remains, which direction should the friction vector be pointing? Remember that friction opposes the direction of motion, and since this box is sliding down the plane, the friction force should be pointing up the plane. And so that corresponds to the free body diagram in A. Okay, so given that free body diagram, we can see that 2 out of 3 of these forces would align naturally with an X and Y axis which is tilted, and so we're going to use that for our coordinate system. And then we're going to determine the work done by each of these 3 forces. The first one is pretty easy to deduce. What work is done by the normal force? Well, the box is sliding down the plane, which is a direction perpendicular to the normal force. And in our equation, work time equal force times distance times cosine of theta. When theta equals 90 degrees, then there's no work being done. So that corresponds to choice C here. Okay? What about now the force of friction, though? Clearly, this is not perpendicular to the displacement. At what angle is the friction pointing with respect to the displacement? So the displacement vector is going to maybe look something like this, right? Okay, with a displacement vector pointing down the plane like that, then I can see that theta between the friction force and the displacement vector, theta is going to equal 180 degrees. So in work equal FD cosine theta, I'm plugging in 180 degrees, so that results in a -1. Okay, so I can see that this is going to be less than 0, i.e. negative. What about the weight force? The weight force, let's draw that displacement vector once again. Now, the weight force is pointing straight down, but it has a component which is in the same direction as the displacement. And another way to think about that is simply to just say, well, this angle here is an angle which is less than 90 degrees. You can see that quite plainly. And so it's going to have to give me, in this equation, FD cosine theta, it's going to have to give me a value which is greater than 0. So we're going to have a positive value for the weight, the work done by the weight. Okay, so let's examine each of these works in turn. We've already said the normal force does no work and that the friction force should be less than 0. It should be negative. So the question then is, what is the amount of that force or that work? So we want to quantify what the friction force is. Based on things that we have learned before, we know that the friction force should be equal to mu times the normal force, and our previous inclined plane problems have probably given us enough practice to figure out what that normal force is going to be. But just in case, if I sum the forces in the y direction, I've got the normal force pointing up, and I've got mg cos phi, remember we're calling this phi now, pointing in the negative y direction. And that's going to equal 0 if this thing is moving at a constant speed, so that the normal force is mg cos phi. Okay, so with that in mind, I can see here that the friction force is going to be mu times that normal force, and phi being equal to 30 degrees tells me that choice A is what I need. Okay, so what about the weight force? Let's draw that displacement vector one more time here. Okay, and here is this angle. Now this angle plus this angle here that's indicated as 30 degrees right beside it, together they give me a right angle, correct? So that means this must be 60 degrees. Okay, so when I'm looking to figure out that work done by the weight equals force times distance times cosine of theta, that's going to give me the force is mg, the distance is d, and what is the angle between the weight and the displacement? Well, that's cosine of this angle, 60 degrees. Okay, now that corresponds to this choice right here. It turns out that that also equals sine of 30 degrees because these are complementary angles. Another way you could think about that, instead of thinking about it the same way that we just did, is to think about the component of the weight force that's involved here, and then you would see that choice C would also be correct. Okay, so E is the correct answer here then, more than one. Okay, so then we want to figure out what the net work is based on the work done by each of these three forces. And I'll give you a minute if you want to pause the video, go ahead and crunch the numbers, and when you come back we can talk about what the answer is. And so if you've done that and you've crunched the numbers, hopefully you've been able to determine that choice C is correct. To go over why that is the case, let's plug in our numbers. For the normal force, we said that there was no work done. For the friction force, we said that it would be mu times the normal force, mg cosine of 30 degrees, times that distance d. When we plug in the values here with the masses given, we get a negative 5.1 joules. For the weight force, we decided that it would be mgd cosine 60 degrees. Plugging the mass and distance in there, we get a positive 29.4 joules. Adding these three things up, 0 plus a negative 5.1 joules plus a positive 29.4 joules gives us a final value of 24.3, which is what we saw on choice C. Okay, and so that concludes all I wanted to discuss today in terms of Unit 3. Next time, we will start to make a connection between work and energy. Thank you.